All right, so in this video, we're going to show how to use a few of the hypothesis testing features in R using our studio here. So we're going to do four tasks, right? So first, we're going to look at how to test the hypothesis that the mean is equal to a specific value in a single sample. Then we'll do the same thing for a proportion. And then we're going to do two more tasks where we'll be testing whether the means are the same or different across two samples. And then again, doing the same thing with the proportion. All right, so let's go ahead and get rolling then. So the first thing we're going to need, now I already have here in our studio, I have a couple of data sets that I have uploaded. So one of them is the unemployment rates that have been observed in Canton, Ohio, which is close to where I live, over some period of time. You see I have here 25 months of data here. And I believe, that if I recall correctly, I took this just as a random sample. Then I have another set, which I'm just calling tests and homework. Right, so this one I have test scores for two different sets of students. One set of students that did all of the homework that was related to that test, and the other for a set of students that did not do all of the homework that was related to that particular test. So you can see there what those values look like. All right, let's go ahead and get started. So the first thing, I did start an R Markdown file here. So I'm going to do the first one. So I'm just going to call this section, it's a single sample mean hypothesis. There we go. That's good enough. Okay, so the code here, in order to do this, I'm going to apply the Canton unemployment data here, right? So I'm going to first load in to df, that is for our data frame, the Canton unemployment data right there. And this is just so then the next lines of code can just be generic. I don't have to keep typing Canton unemployment. I can just use the F instead. Okay, so to do this test, it's actually remarkably simple. It's like for R, this is amazingly simple, and it's a single line of code. It's t.test, right? So what that is going to do, it's going to do a hypothesis test based on the student's t distribution. Now, technically speaking, when you are doing a test for means, you can use the normal distribution if you have at least 30 in your sample. However, there's nothing wrong, right, with doing the t-test. I think it's one of those things where as long as your standard deviation is unknown, so you're basing it on the sample, technically the t-test is correct. It's just that conventionally we would revert to the standard normal distribution for a large enough sample just because the standard normal distribution is well known. But now that we have computers able to do a lot of the work for us, it really doesn't matter. We can do what is actually technically correct, um, even if it might technically be difficult in terms of computation, because we as human beings aren't doing the computation. Right, so t-test is our function. So then I need parentheses to start putting things in. The first thing that I need to put in would be the data itself. So in this case, df would be our data frame. Okay. Then the next thing we do now, if I have more than one variable that I'm looking at, I would then put in y equals and then whatever the second sample is. We're not doing that. This is a single sample, so df is enough. It just has one column in it, right? So I don't have to worry about specifying which column. If you did need to do that, you do df and then the dollar sign and then choose the appropriate variable. The next thing I need to do then is to choose the level that I'm going to be testing. And I think that there's a perception that 5% or so is about typical for unemployment rate. So I'm going to test whether that is actually the case. So mu equals 5, so it's mu equals 5. So this is just me saying what value I'm testing against. So it's going to then run a hypothesis test to find out, is the sample mean in the sample that I'm giving it significantly different from 5. That's what I'm telling it to do. Now, there are other options we could throw in. So, for example, I might want to specify what the alternative hypothesis is. So that would be another option I could put in. So to do that, I just do alternative equals, and then in quotation marks, I have a choice of three things. So one is two dot sided. So that means that the thing that I'm testing is whether the mean is equal to a particular value, which is what I'm doing here, in which case the alternative would be two-sided. It's not equal to, it is either greater than or less than. Now you also have the option for alternative to put in greater or less as the other options if you wish. Now the default here is two-sided, and that's what I'm doing, so I technically don't have to include this option, but I will include it there just for you to see. Now there are some other options we could include as well. They're really not relevant here. Most of them are um, relevant to if you're doing a two-sample test. I guess the only other thing here that I might possibly want to do is to define what my confidence level is, but that's if I care about the confidence interval that it's going to calculate. That's not what I'm here for. I'm here for the hypothesis test. So let's go ahead and run this chunk of code. I'm just going to hit the play button here, let it run, and there we are. So looking at the output here, so the first thing it's going to tell me is what the data is. So this df, that's just telling me where it's reading the data from. Okay, that's not particularly informative. It's just saying what I put into the thing. Then the next line is where we get some information that is potentially useful, right? So this t value. So this is what it calculates, which is equal to, right, your sample mean minus the hypothesized mean divided by the standard error. Now the standard error would be that standard deviation divided by the square root of your sample size. Right, so in this case, t equals 3. Now, interpreting this directly is hard to do because it depends on your sample size. Now, if you have a really big sample, then a t around 2 or so, or -2 if you're looking at negatives, but the um, the magnitude of about 2 or higher would indicate a substantial difference or significant difference from the hypothesized value. Okay. Then df here, this would be your degrees of freedom. It's just your sample size minus 1. So this is just telling me that I had 25 in my sample. Right, so it would be a bit short of the 30 we normally would use to revert to a normal distribution. Okay, and that is also just a way I can use that if I want to look up on a t-table to find out what the appropriate cutoff value is for the t, but that's really not necessary. Like, this is something that I think in some ways this is a relic of an old time period when it was harder for us to get precise calculations for the p-value. Now it's not because we live in an age where computers are pretty easy to use and are pretty advanced. So the p-value is really the thing we'll focus on. I think it's the most useful thing for us because that p-value has a clear interpretation that can be, in effect, universalized across tests. So what the p-value tells you is what is the probability of having a value at least this far, right, from your null hypothesis if the null hypothesis is true. Right? So that means then is that if the mean, the true population mean, right, for Canton unemployment rate is actually 5, probability of me seeing what I actually saw, which we can see our sample estimate at the bottom here, that's a 5.544, probability of me seeing something that far away or further from 5 is point, okay, so it's 0.00591, so it'd be about 0.591%, right? So less than 1% chance. So what that really means is that the data here is not very consistent with that null hypothesis that the mean is equal to 5. So the way we would interpret the p-value in terms of, like, we know the technical meaning is this probability of being at least as far from the null hypothesis if the null hypothesis is true. That's not very intuitive. The way that I would interpret this intuitively is that it's a measure of consistency between the data and the null hypothesis, right? So if your p-value is equal to 1, that will happen if your sample mean matches the hypothesized mean exactly, right? So in that case, we're 100% consistent, right, with that null hypothesis, right? So we are less than 1% consistent. So the way that we would normally use this is first, remember with hypothesis testing, we have a bias toward keeping that null hypothesis. We're really looking for evidence that it's definitely inconsistent, the data is definitely inconsistent with that null hypothesis. So what we're really generally looking for is a p-value less than 5%, 0.05. So in this case, we're definitely well below the 0.05 cutoff, which tells us then that Yeah, the null hypothesis is not true. The data just is not consistent with it, so we would reject the null hypothesis. Other data, other parts of the output. So alternative hypothesis, this is just stating what the alternative hypothesis is. And this is really just letting us know, are we looking at that greater than, less than, or are we looking at a two-sided test? So true mean is not equal to 5, so it's a two-sided test. Now the confidence interval is here. Now there is actually a connection between a two-sided test and the confidence interval. And that is, right, with a confidence interval, we know then there's a 95% chance the true mean is within this range. Well, if the hypothesized value is not in that range, then we know that we would end up rejecting that null hypothesis. So in this case, our hypothesized value is 5. It's not within the 95% confidence interval. That means uh, there's a significant chance, we'll just say, that it's not going to be 5. All right. And then finally, the sample estimate here says the mean of x. So since we only have one variable in there, right, so this would be, in our case, the Canton unemployment rate. So the mean in the sample was 5.544. So that is how we do a one sample a t-test for means using, so just a couple lines of code, and that's it. All right, so let's go ahead and move on to the next task, and we'll do some proportion stuff. So I'm going to start a new chunk here, right? And it's R, and this is going to be single sample proportion hypothesis. All right, and then I'm going to put in remember those are the slanted apostrophes you find in the upper left corner of your keyboard. It shares the same key with the tilde. All right, so in this case, we're going to use a different uh, function. It's prop.test. This one, I'm not actually going to load any data in. I don't have to. So all I need to use this test, when you're doing a proportion test, I need to know the number of successes, that is, how many observations in my sample had the trait that I was looking for. And I also need to know what is the number of observations total in my sample. And so let's just consider a simple case. Suppose that I am flipping a coin and I want to figure out, is this a fair coin or not? Right, so naturally, if it's a fair coin, then half the time it will turn up heads, half the time it will turn up tails. So let's just propose, right, that I flip this coin 300 times. And 160 times it comes up heads. Right? So it's not quite exactly 50%. Now, the question then is it close enough to 50% that I'd still consider it to be a fair coin? All right, so let's go ahead and do this. So we've got prop.test is the function we're going to be using. And then in there, the first value that I'm going to put in is the number of successes. So in this case, it's the 160 heads. The second thing I'm going to put in here is the sample size, which is 300. The next thing is whatever my hypothesized value is. So in this case, it's p equals zero point 0.5. Because I think and hope that it's a fair coin. So that would be a zero point 0.5. So P equals indicates that you're putting in a proportion that you're going to be testing, and zero point 0.5 would be the value that we're looking at here. Now, again, I can, if I wish, I have a couple other options I can put in. I can specify my alternative hypothesis. I'm going to go ahead and do that, even though it's not necessary for me at the moment, because I am doing what is the default. Right, so again, two dot sided, right, is what I'm doing here. So I'm really testing, is the proportion equal to zero point 0.5? If it's not equal, whether it's greater or whether it's less, it doesn't make any difference to me. Right? So not equal would be my alternative. So it's a two-sided test. And again, I could also specify the confidence level if I wanted to. I'm not going to bother to in this case because I'm not really interested in that confidence interval. All right, so I'm going to go ahead and run this code. So again, a single line of code and run it. Now, one thing I will say, some of these tests are things you can do in Excel. For example, if you use the data analysis tool pack in Excel, then it can do uh, the means kinds of tests, but it's actually kind of tricky to set up if you're testing against a specific value. And actually, Excel is not very well designed for dealing with proportions at all. You actually have to create an Excel template. Meanwhile, in R, single line of code, I really only had to define kind of three things: number of successes, I need to define the number of observations total in the sample and what the proportion is I'm testing against, and that's it. It'll perform the test. So here's what we've got. So the output here is very similar to what it was in the other. All right, so things will point out here. So I'm not going to worry about too much here except for this p-value. P-value is really the key here for what we're looking at. Right, so p-value 0.2727. So it's telling us that there's a roughly 27% chance of ending up with a result this far from a proportion, exactly 50-50 proportion, right, if it's a fair coin. Now remember, we give the benefit of the doubt in effect, right? So I'm going to be somewhat tolerant here and say, well, for me to reject the idea that it's a fair coin, that is, that the true proportion is 50%, I would need this to be less than 0.05. That's the typical number. Now, sometimes you'll see zero point 0.1 used, sometimes you'll see zero point 0.01 used, but I'm going to stick with 0.05 or 5%. In this case, right, our p-value is above that, which means our data is more consistent with the null hypothesis than it has to be for us to go ahead and not reject it, to say, well, we don't have sufficient evidence that it's not true for us to reject it. So we'll go ahead with the null hypothesis. We can also use the confidence interval here. Right? So zero point 0.5 is very clearly within that range. Right? So it is possible that this is a fair. It also provides the sample estimate here, so we did see that 160 out of 300 is basically 53%. Okay. All right. Now, well, I guess I'm going to just make a quick note here. Uh, One thing that I think about is one, there's statistical significance, and that's really all about that p-value. Is the p-value less than 0.05? If the answer is yes, then our sample shows that there's a statistically significant difference between the hypothesized mean and the true mean. Right? But then there's also the practical difference, right? So, all right, we have so even if we find that there's a statistically significant difference, it might be that we're still close enough that it wouldn't affect our decisions in any significant way. Now, that does suggest we might need to rethink our hypothesis. If it's not going to affect our decision, why are we gathering the data? Is a fair question. But I think it is worth remembering at the very least. Okay. All right. So, next line here. All right. So, I'm going to go ahead and start another chunk, and we're going to start doing some two sample tests. Right. So, R is going to be a two sample mean hypothesis. So, what we're going to do here, I'm just going to give myself a little bit of space underneath this as well. What I'm going to do now, I'm going to load in some new data. And so our new data frame here, right, this is going to be that tests and homework. We have one column for those that did all the homework, one column for those that did not do all the homework. There we go. All right, so now what I want to do is I'm going to use that t-test function again, but rather than testing against a specific value, I'm testing whether the means were the same. Now here there are additional options we could think about. So I'll talk about those a little bit. We're going to end up going with what is the default anyway, but I at least want to mention them. Okay, so t.test. Here we go. So first thing I need to do is put in my first data set. So it's just df, right? And okay, so it still has the old df in there. So this u3 is not what I want, right? So what I'm actually going to do, well, let me do this first, okay, just so that I get the right options here. I'm going to go ahead and run the chunk before I add t-test to it. And that's just going to change what's in that df data frame. That way, now when I go through and I type t.test df, now it's giving me the options that I want. Okay, so well, first, those that did all the homework would be the first set that I'm looking at. And then I'm going to set y equal to, this is saying I want a second variable that I'm looking at. And that's again df $, and those that did not do all the homework, which I just have did not here. Okay, right, so I've got my two different options in here. I could actually run it right now because everything else I'm just using the defaults. Right, so now I'm going to go through and show what those defaults are, just so you know the things that you can switch if you wish. Right, so one thing you can do, which I'm not going to add in, is you can actually define what you think the difference is going to be. So very much like we did mu equals 5, you could put mu equals to whatever you wish. If you leave it out, it's assuming 0, which what that means is I'm testing, are the means just different from each other? Not are they different by at least a certain amount. Okay, so that's one thing. Uh, so I'm just going to leave that one blank. I can also, again, define the alternative hypothesis. In my case, because I'm looking at whether they are equal or not, again, two-sided is what I want. Okay. A couple other things we can do, right? So one option is you can run what they call a paired test, right? So what a paired test does is it takes each point in your one set of data and pairs it with the corresponding point in the other set of data in order. Right? So pair the first with the first, second with the second, third with the third. And what it's really trying to do is say, right, do we see a difference, right, as we move from this first to the second data set along each line? This is something that is clearly inappropriate in this case because what it requires is that there be some kind of natural pairing between your two data sets. That doesn't make sense here because, for one, our data sets, these data series, are not the same size. I've a different number of people did all the homework than did not do all the homework. There's no way for me to pair these things. So I'm going to just make paired equals false, indicating that I'm not pairing the data. Now, where this is more appropriate, the most common case is if you have um, a before and after. That's really the best case, right? So if, for example, I gave my students a pre-test and then a post-test for that same set of students, right? So before we took the course, take a pre-test, see what your knowledge is when you come in. At the end of the course, take a post-test, see what your knowledge is as you leave, and then I look at the scores for the before and after. In that case, there is a natural pairing. I can take, student A, so Billy, right, got this score on the pre-test, this score on the post-test. Obviously, I want to pair those two together. Sometimes you can also do this artificially. So, for example, if you run a marketing campaign in, say, 20 different cities, where 10 get one particular marketing campaign, 10 get a different marketing campaign. If you choose carefully, then you can say, oh, well, this city is very much like that city in terms of the demographics, the size, this kind of stuff, right? So they kind of naturally would pair together, and that allows us to compare, was marketing campaign A or B better, right? So you can create these pairings intentionally, but it really requires a design to make that happen. Right, so in a case like this where I did not try to create such a design, this is not a before and after. I did not try to make sure that everybody who didn't do all the homework had a natural pair with somebody that did all the homework in terms of other things that I care about. No, pairing is not going to make sense here. The other thing that you can possibly use is var dot equal. So this is what you would use. You'd set this to true if you have reason to believe that the variances in your two samples will be the same. In my case, I honestly think they wouldn't be, so I'm going to put it to false. And I will say false is again the default. So basically everything after did not, I don't actually have to put in here because I'm just using defaults. The default for alternative is two-sided. The default for paired and for variance being equal is false. So if I had left those out, it would run exactly the same test as what I'm running right now. I just want you to see these. Right, so if you are in fact pairing, then you can set paired equal to true, in which case you don't need to worry about whether the variance is equal. And if you think the variance is equal, you can set that equal to true, and you don't have to worry about pairing because it's naturally going to set to false. Right? So it'd be kind of weird for you to always lay these out as explicitly as I am, just because you don't have to. Right? So, but I wanted you to see them to know that they're options. All right, so I'm going to go ahead and run this. And there's our result. So again, very much like with the one sample test, right, we have that it calculates the t-value, and how it calculates this one is that it takes the sample mean for one of the sets of data, sample mean for the other set of data, subtracts them, and then divides by a standard error that it's going to calculate. The algorithm here is a bit tricky because we have two different samples with different sizes, so it's not quite as simple as, oh, just take the square root and just take the standard deviation divided by the square root of the sample size. We have multiple sample sizes that we're going to have to adjust to. You can see here the degrees of freedom it's using is actually a fraction. that's really trying to combine these two different sample sizes and also accounting for the fact that the variances are not the same. What we can focus on though, right, because again, we don't have to worry about all that stuff because we have the p-value given to us. Right? Remember again, the key value that we're comparing to is 0.05. If we're above 0.05, they're close enough that we don't have good evidence they're different from each other. In this case, we're definitely less than 0.05, less than 5%. That tells us that the data is not consistent with the means for these two groups of people being the same. So we would reject that idea, saying, no, they are not in fact the same. Right? There is a significant difference between the two. Now, which direction does that go? Well, the hypothesis test in itself doesn't tell us, but we can just look at the means. This looks like the mean for x being those that did all the homework, the first thing that I put in, was higher than the mean for y, those that did not do all the homework. And it looks like on average there's about a 10-point difference, right? So that's I think that most people would say practically that is a significant difference. Right? And it is also statistically a significant difference as shown by the very low p-value, less than 0.05. Right, now let's do one last test. So we're going to do the same kind of thing, but now applied to proportions. So create this chunk. So R, not 4. All right, so it's again a two sample. In this case, it's a proportion hypothesis test. Right, and then close out the chunk here. And this one, again, we just need one line. It's prop.test again. Now, in order for us to do two samples, what we need to do is have a vector that we're going to create for the number of successes and also for the sample size. Now, this is very easy to do. It's just the C function. It's technically, I think they call it, it's a concatenate function or something like that. No, it's not technically concatenate. I'm not sure what it is, what the C stands for. But there we go. So the C function is what we need. So what we'll do, so let's look at a specific case, right? So the case that I'm imagining here, it's a very common uh, case that we work with of A/B testing for marketing. This is a very common strategy, especially used in online marketing, where the marketing department comes up with two different ads. Right? One of them will call it ad A, the other will call ad B. Right? And then your algorithm will randomly assign either A or B, right, to various people as they see whatever the website is this ad is on. And then what you do is you track how many clicks you get. Right? So we know the number of people that are viewing the thing because we know how many times it's being shown. We track that. And then we also know how many clicks we get for that ad. Right? So we're really interested in is the click-through rate. So what proportion of viewers actually click? Right? So in this case, a success would be a click, and the sample size would be the number of views. Right? So let's say that we have done this. Right? So we have two different ads. Let's say the first ad, it gets 5,217 clicks. Right? The second ad gets, oh, let's just say 4,538 clicks. Now, this in itself, even though that feels like a big difference, that doesn't prove a difference because I've not yet accounted for the number of views, right? So for that, we need a comma out here. So we have first defined our successes for the first sample and the second sample. Now, again, using that C function, we need to define our sample sizes. So let's say the first ad happened to have been shown 41,654 times, while the second ad was shown 36,854 times. Okay. Right? So we do see there are more views and more clicks, right, for that first ad, fewer views, fewer clicks for the second ad. Now, does this balance out to favor which ad over the other? It's not clear. It's not clear that even necessarily there is a difference. So that's one thing. Now, other options here, big one that was actually going to be useful is that alternative. So alternative equals, okay. Again, I'm going to do two-sided in that I don't really have a preference for one of these ads over the other. Neither of them would I consider to be a default over the other that I need to prove the other one is better. Right? So in that case, I'm going to do two-sided here. I could again make this greater or less depending on the specific um, test that I'm going to do. In this case, two-sided, I'm just looking to see is there a difference or not. If there is a difference, then we can see which one was that had the higher click-through rate. All right, so let's go ahead and run this test. So we'll just go ahead and hit the run button here. And we've got it. Okay, so again, the p-value would be the first thing that we really look at here. So is there a significant difference here? Remember our cutoff is 0.05. Anything less than that indicating that there is a significant difference between the data and the hypothesis. In this case, the default hypothesis is that there is no difference between these two ads in terms of the proportions we're calculating from them. Uh, well, I mean, our p-value is greater than 0.05, which means the data is sufficiently consistent with that null hypothesis to say we don't have evidence that there is actually a significant difference between the two. They, they look basically the same as far as we can tell. And again, we can confirm this. And one, the 95% confidence interval spans 0. So 0 would be right in between here. So that indicates very possible there's no difference at all. And also, when you look at our sample estimates, these two are actually very close together just at a glance from to my human eyes. We have 12.5% click-throughs over here versus 12.3% click-throughs over there. And it doesn't look like a big difference. And in fact, this is also confirmed in the statistics that statistically it is not a big difference. And now, naturally, I still might want to say, oh, well, let's push add A because it was the one with the higher proportion, but I wouldn't expect this to make an enormous difference. Okay, so I could consider other things with which add I want to show. All right, so that then covers those four tasks. So we've looked both at one sample and two sample, both for means and for proportions. How we can do that in R, I think it's fair to say that in terms of the coding, this isn't outrageously difficult. It's just that one line of code. I think hypothesis testing is one of those things where, in my mind, the hardest part, right, is thinking about how to set the test up in the first place. Right? And that's really a human task. Right? Taking it to the computer, having the computer do the calculations, that I think is relatively straightforward.